When you look up at the night sky, it's easy to forget that every tiny spark of light belongs to something vast beyond imagination. Our home, the Milky Way, looks like a faint mist across the dark, but that mist is made of hundreds of billions of stars, each with its own story. For a long time, we didn't truly know how big our galaxy was, or where exactly we stood inside it. Now, for the first time, we're beginning to measure its true shape and size, stretching more than 100,000 light years across, wrapped in a halo of invisible matter that extends even farther. Tonight, we'll travel through that cosmic landscape together, tracing the spiral arms of our galactic home and discovering what lies beyond them. Settle in, take a moment to breathe, and if you enjoy exploring the universe with us, feel free to like and subscribe before we begin our journey. Right now, you are moving through space faster than you could ever imagine. More than 500,000 miles every hour carried along on a slow, silent ride around the center of our galaxy. The Milky Way stretches wider than light, can travel in 100,000 years. It holds about 400 billion stars, and our sun is just one of them. We live inside this spinning island of light, but no one has ever seen it from the outside. We have never stepped far enough away to grasp its full shape. What we know has been pieced together from light and motion, from careful measurements taken over generations of quiet watching. Astronauts sometimes talk about the first time they see Earth from orbit. They press their faces to the small round window and search for home. They look for city lights, for a familiar coastline, for the curve of a mountain range. From up there, the world they know becomes small. Cities that once felt endless shrink into faint clusters of light. The wide rivers, deserts, and forests blend together until the whole planet looks like a single living surface. At just a few hundred miles above the ground, the details of daily life disappear. A house, a street, even a city block, none of it is visible anymore. The distance is enough to erase everything that once felt close and solid. This shows something we rarely think about. Distance changes what we can see. When we rise high above Earth, the edges between things blur. The details fade until only shape and color remain. From that distance, even something as large as a country becomes a patch of green and brown, soft and undefined. And as we keep pulling back, the planet itself becomes a sphere. From 10,000 miles away, it turns into a glowing marble against a black sea. The Earth, that once seemed endless under our feet, now fits in a single frame of vision. Yet, as our world shrinks, the universe around it grows beyond all understanding. The space between stars, between galaxies, expands into distances so large that the mind struggles to hold them. If you could shrink the Earth to the size of a small marble sitting on your desk, the nearest star would be thousands of miles away, farther than the drive from New York to Los Angeles. That marble would sit in an ocean of emptiness so wide it feels impossible. The scale of the universe is not only about what is big, but about how much space lies between those big things. The emptiness is real. Our planet floats in a sea of vacuum so vast that even light, the fastest traveler in existence, needs years to cross from one point of interest to another. Light moves at 670 million miles an hour, yet the stars in our sky are so distant that their glow must race through space for years, centuries, or even millennia before reaching us. Still, we are not alone in that silence. Our tiny world is part of something larger, a vast collection of stars, planets, and invisible matter moving together through space. This is our galaxy. But seeing it, truly seeing it, is impossible from where we are. Just as astronauts cannot spot their homes from orbit, we cannot step far enough back to look at our galactic home all at once. We live inside it, bound to its spinning arms. When we study it, we do so through traces of light that have traveled across impossible distances to reach us. The light entering your eyes right now has been on a journey far longer than any human voyage. The nearest star beyond our sun is called Proxima Centauri. Its light takes more than 4 years to reach Earth. That means the light you might see from it tonight left that star when the world below you was already years younger, when people held different jobs, when songs on the radio were different, when seasons had yet to turn. The photons have crossed the dark, empty space for 4 years, moving unbroken, just to arrive here in this moment. For a sense of scale, think about this. When Christopher Columbus sailed from Spain to the Americas in the 15th century, his journey of roughly 4,000 miles seemed endless to those who lived then. That distance marked the edge of the known world. Yet the light from Proxima Centauri travels 25 trillion miles to reach us. 25 trillion. If you drove a car at highway speed without ever stopping, day after day, year after year, it would take more than 40 million years to reach that single star. This is the scale of our cosmic neighborhood. Those tiny specks of light scattered across the night are not small at all. Each one is a blazing sphere of gas and energy, some larger and brighter than our sun, some smaller and cooler. They look faint only because of the impossible distances that separate them. Between stars lies so much space that light itself, moving faster than anything else, must spend years crossing the gap. The Milky Way holds about 400 billion of these stars. Some are close, just 4 light years away, like Proxima Centauri. Others burn tens of thousands of light years from us, their light taking longer to arrive than human history has existed. Many of those photons left their stars before humans appeared on Earth. Some began their journey before the first dinosaurs. When you gaze at the sky, you are not just looking outward, you are looking backward in time. The night sky is a kind of memory. The light you see now carries messages from the past, from stars that may have already burned out or changed forever. Their final light still travels toward us, filling our eyes with a view of what once was. In that way, the sky is both ancient and alive. Every glimmer is a record of something that happened long ago, still unfolding above us. And here lies the quiet truth. We can never see our entire galaxy at once. We are inside it, too close to the light, too bound to its turning. Our instruments trace its spiral arms and measure its rotation, but we remain like small creatures walking across the face of something enormous. We can touch a small part of it, map the stars nearby, sense the direction of its motion, but we cannot yet step back to witness the whole. From our place inside, the Milky Way is both home and mystery, a vast clockwork turning in silence, its edges forever beyond our view. The light from the far edge of our galaxy has been traveling toward us for 100,000 years. It carries quiet messages from places so distant they could belong to another reality altogether. That light is still on its way, crossing the silent reaches of space, moving through dust clouds and star fields until it finally arrives here, in this moment, after a journey longer than human history itself. Now imagine holding a single grain of sand between your fingers. It's small, about 1 millimeter across, almost weightless. You could drop it into the carpet and never find it again. You could blow it away with a gentle breath. It is one of the smallest things you can still see and feel without help. For a moment, let this grain of sand represent the entire Earth. Every mountain, every ocean, every city, every person, everything that has ever existed compressed into that tiny speck. On this scale, your home vanishes, your neighborhood disappears. Even great cities like New York or Los Angeles shrink to invisible bumps you would need a microscope to detect. If the Earth becomes that grain of sand, then the moon turns into a small pebble floating 20 feet away. The sun becomes a bright beach ball resting half a mile down the road. Jupiter swells to the size of a large marble rolling around 3 miles from where you stand. These distances may sound simple, but they already stretch beyond what our senses grasp. Half a mile feels close. 3 miles already asks for effort. Yet the nearest star, Proxima Centauri, would now sit 125,000 miles away. In this sand grain universe, you could not drive there, not even fly there. You would need a spacecraft just to reach the next closest sun. This simple model shows how truly empty space can be. The gaps between planets in our solar system already seem enormous, yet compared to the distances between stars, they are almost nothing. On this scale, our whole solar system fits comfortably within a circle about 10 miles wide. But the next solar system waits 125,000 miles away, roughly 12,000 times farther than the full width of our planetary neighborhood. Between those islands of warmth and gravity lies a darkness so wide and so empty that it defies imagination. Even these great distances fade beside the size of our entire galaxy. If we keep this same scale Earth as a grain of sand, the Milky Way stretches about 11 billion miles from edge to edge. 11 billion miles. Light, racing at 670 million miles per hour, would need 16 hours to make that trip. That is the size of the place we call home. And still, this comparison shows only distance. It leaves out the other part of our story, the movement. As you sit here, you are moving faster than any machine humankind has ever built. You are not only spinning with the Earth's rotation, turning eastward at about 1,000 miles per hour. You are also riding along as the planet orbits the sun at 67,000 miles per hour. Yet both of these familiar motions are tiny compared to the speed of the entire solar system itself. Together, the sun, Earth, and all our neighboring planets hurtle through space at more than 560,000 miles per hour as we circle the center of the Milky Way. It's a motion too smooth to feel, too steady to sense. The fastest jet fighters reach around 1,500 miles per hour. The old Concorde passenger jet once cruised at about 1,350. A rocket leaving Earth might reach 25,000 miles per hour to break free of gravity. But every one of us, even when sitting quietly in a chair, already moves through the galaxy at speeds far beyond any of those numbers. We live our entire lives in motion, carried across the stars on a path so vast that we measure its turns not in days or years, but in tens of millions of centuries. The scale of it all, from the grain of sand to the span of the galaxy, tells us something about where we belong. Space is not crowded. It is ruled by distance, by quiet movement, by stretches of emptiness that make our small world feel fragile and extraordinary at once. And inside that immensity, stars gather in patterns shaped by gravity patterns that give our galaxy form, structure, and meaning. Understanding how those shapes hold together will bring us closer to seeing what the Milky Way truly is. What gives us such incredible speed? We are in orbit. Our sun, along with its planets, moons, asteroids, and comets, circles a massive center of gravity located about 26,000 light years away. We move around it like a stone on the end of a string, but this string stretches across distances so vast that light itself would need 26,000 years to travel from one end to the other. This long journey defines our place in the galaxy. One full orbit around this invisible center takes roughly 250 million years. When our solar system last passed through this same region of space, there were no dinosaurs. The first forests had only just begun to form. The continents that would one day become the modern world were still fused together in a single mass called Pangaea. At that time, the planet's oceans were home mostly to simple marine life. Since Earth formed about 4.5 billion years ago, our world has completed only about 18 of these galactic orbits. We can say, in a sense, that Earth is 18 galactic years old. That number places our existence in perspective. All of human history, from the first chipped stone tools to spaceflight, has unfolded during less than 1% of a single orbit around the Milky Way's center. Every empire that rose and fell, every language that was spoken, every life that came and went, all happened while our solar system moved through only a tiny arc of its path around the galaxy. Civilizations appeared, flourished, and disappeared in what amounts to a single moment on the cosmic clock. At the heart of this great orbit lies something powerful enough to keep hundreds of billions of stars moving in a coordinated dance. The question is simple. What could possibly anchor such a vast system? What kind of object holds so much gravity that even the sun and its planets must bow to its pull? The answer leads us towards something so extreme that it bends the structure of space itself. For most of human history, people believed that Earth sat at the center of everything. The sun, moon, and stars seemed to circle us with perfect regularity. It was an idea that matched both experience and comfort. We could feel no motion beneath our feet. We watched the heavens rise and set like clockwork. It made sense to think the cosmos revolved around us. That view lasted for centuries, until new instruments began to reveal a different truth. Careful measurements showed that Earth was not fixed at the center, but instead orbited the Sunday. This discovery shifted our place in the universe, but many hoped that perhaps our sun itself sat near the middle of something larger. That hope would not last long. In 1917, astronomer Harlow Shapley studied the sky with a precision no one before him had achieved. He focused on globular clusters, dense, round gatherings of ancient stars that hover around the Milky Way. By measuring their distances and plotting their positions, he uncovered a surprising pattern. These clusters were not arranged around our solar system, nor around any nearby region of space. They formed a sphere centered about 30,000 light-years away, in the direction of the constellation Sagittarius. The meaning was clear. Our sun was not near the center of the galaxy. It sat far from it, roughly 2/3 of the way out toward the edge. In human terms, it was like discovering that your house, which you thought stood in the middle of town, was actually located on the outer edge of the suburbs. Our solar system resides in a quiet neighborhood, far from the bright, crowded hub where stars gather in dense swarms. Shapley's finding changed astronomy forever. It showed that the Milky Way extends roughly 100,000 light-years from side to side, and that we live about 26,000 light-years from its core. His work revealed the scale of our true home and reminded us how small a part we occupy within it. Being in this outer region turns out to be an advantage. The center of the galaxy is an extreme and dangerous environment. It is filled with strong radiation, powerful magnetic fields, and violent gravitational forces. Massive stars collide and die there, releasing bursts of energy that can sterilize anything nearby. Our position, far from that chaos, allows stability. Here, the conditions are calm enough for complex chemistry to persist, for planets to hold atmospheres, and for life to evolve slowly over billions of years. Still, Shapley's discovery raised another mystery. If we orbit something about 30,000 light-years away, what could possibly have enough mass to hold the galaxy together? What kind of object can bind hundreds of billions of stars into a single spinning system? At the time, no one had an answer. The technology and data simply didn't exist to see what lay hidden at the galactic core. And even if we could look, the challenge would remain immense. Measuring the size and shape of the Milky Way while living inside it is like trying to map a forest while standing among the trees. We can see the nearest trunks clearly, but the outlines fade into distance and darkness. Astronomers faced that same problem when they tried to measure our galaxy. They could chart the local stars, but the far edges remained hidden behind clouds of dust and gas. To understand the true size of the Milky Way, they would have to find new ways to see through that obscuring veil and uncover what lies at the heart of our cosmic home. Harlow Shapley faced a problem that no one before him had solved: how to measure something so enormous that you could never step outside it to see its shape. He knew that he would never view our galaxy from the outside, so he found a way to map it from within. His solution came through the globular clusters, those dense, ancient swarms of stars that orbit the Milky Way like distant lanterns circling a vast city. Shapley realized that these clusters formed a kind of spherical shell around the galaxy. If he could measure the distances to enough of them and place their locations in 3 dimensions, he could trace the invisible outline of our galactic home. The clusters would act like markers on a cosmic survey map, sketching the edges of something far too large to see directly. That, however, required solving another problem: finding a way to measure distances to objects tens of thousands of light years away. To do this, Shapley turned to a special kind of star called a Cepheid variable. These stars pulse in brightness at regular intervals, growing brighter, then dimmer, like a slow and steady heartbeat. The time between those pulses reveals something remarkable: how bright the star truly is. A Cepheid that pulses slowly is intrinsically brighter than one that flashes more quickly. This predictable rhythm became Shapley's ruler for the cosmos. By measuring how quickly a Cepheid pulsed, he could determine its true brightness. Then, by comparing that intrinsic brightness to how faint it appeared from Earth, he could calculate its distance. The dimmer it looked, the farther away it had to be. Using this technique, Shapley measured the distances to dozens of globular clusters scattered across the sky. When he plotted them, a pattern began to appear. The clusters formed a vast, roughly spherical region about 100,000 light-years wide. Our solar system was not near the middle of that sphere, but out toward its edge, about 2/3 of the way from the center. This finding shocked everyone, even Shapley himself. 100,000 light-years was far beyond any previous estimate of galactic size. Before his work, most astronomers assumed the Milky Way might stretch only a few thousand light-years across large, but still within a scale of nearby stars. Shapley revealed that our galaxy is truly colossal. Light, traveling at 670 million miles per hour, would need 100,000 years to cross from one side of it to the other. His measurements, made with early 20th century instruments, turned out to be astonishingly accurate. Modern refinements have adjusted some details, but his basic scale still holds true. Even so, Shapley's map captured only what we can see: the visible stars, the gas clouds, the dust. Something else surrounds all of this, something invisible and far more massive. It cannot be seen, touched, or detected with normal instruments, yet it outweighs everything visible by about 20 to 1. Stars, planets, dust, and gas, everything that shines or reflects light, make up only about 5% of our galaxy's total mass. The other 95% belongs to something we now call dark matter. How can we know it exists if we cannot see it? By its influence. The stars on the outer edge of our galaxy orbit the center far too quickly. If gravity came only from the visible matter, those stars would fly away into intergalactic space like droplets flung from a spinning wheel. But they stay bound, circling steadily. Something unseen must provide the extra gravity needed to hold them in place. That hidden mass forms a vast, roughly spherical halo of dark matter that stretches well beyond the galaxy's bright disk of stars. Recent studies suggest that this halo extends nearly 2 million light-years across 20 times farther than the visible Milky Way itself. In other words, the shining spiral we can observe is just the inner core of something much larger and stranger. Imagine our visible galaxy as a narrow beam of light from a flashlight in a dark room. The dark matter halo would be the entire room surrounding that small cone of brightness. We live inside the beam, surrounded on all sides by invisible matter that we can detect only through its pull on everything else. It doesn't glow, it doesn't block or reflect light. It passes through ordinary matter as if it isn't there at all. Billions of dark matter particles move through your body every second without leaving a trace. They flow through the earth, the sun, and the stars, indifferent to the atoms that make up everything we know. Scientists estimate that the halo around our galaxy holds somewhere between 600 billion and 3 trillion times the mass of our sun in dark matter alone. That invisible weight shapes how the Milky Way rotates, how it forms new stars, and even how it interacts with other galaxies. The existence of this unseen mass changes the way we think about the universe itself. Most of what exists is invisible to us. The matter that builds planets, stars, and people, everything we can touch and see, makes up only a tiny fraction of reality. We inhabit a cosmos made mostly of something we cannot directly detect, a universe where light reveals only the smallest part of the whole. Yet even this vast dark halo has its limits. It marks the outermost edge of our galactic home, the border beyond which the Milky Way's gravity fades into intergalactic space. And just beyond that boundary lies something larger still, an ocean of galaxies, each with its own stars, planets, and halos of dark matter, stretching endlessly into the night. In 1977, 2 small spacecraft left Earth on a journey no human could follow. They were called Voyager 1 and Voyager 2, twin explorers, built to study the outer planets and then continue onward into the unknown. Each craft travels through space at about 38,000 miles per hour, faster than anything else humans have ever launched. At that speed, they could cross the United States in less than 5 minutes. They are the fastest messengers humanity has ever created, still drifting through the darkness beyond the reach of the sun's influence. Their speed is extraordinary by any normal standard, but for the scale of the galaxy, it is painfully slow. If Voyager 1 were aimed toward our nearest star, Proxima Centauri, it would need about 173,000 years to get there. 173,000 years, 10 times longer than all of recorded human civilization. Everything humans have ever built, from the first farms to the digital age, has existed for only a fraction of that time. And yet, even reaching the next star would count as almost nothing in the context of the Milky Way. To cross the entire galaxy, about 100,000 light-years wide, Voyager would need roughly 1.7 billion years of continuous travel. 1.7 billion years. That is longer than the history of complex life on Earth. When we imagine that span, we move beyond history and into deep time. When Voyager would have started such a journey, Earth would have been a planet of single-celled organisms, simple bacteria floating in ancient oceans, long before plants, animals, or oxygen-rich air existed. During the time it would take Voyager to cross the Milky Way, life on Earth evolved from those single cells into forests, animals, and humans capable of building spacecraft. Galactic distances are so vast that evolution itself unfolds faster than travel. This comparison brings cosmic scale into perspective. The leap from one star to another at our fastest speed takes longer than the rise of all civilization. And still, Voyager continues on, powered by its fading nuclear generator. Its fuel is nearly gone. Its instruments grow quiet. Within the next decade, both spacecraft will fall silent. They will keep coasting, drifting forever through interstellar space, mute artifacts of a species that once looked up and wondered what lay beyond. Between the stars, the universe is nearly empty. The space Voyager travels through contains less than one atom in every cubic centimeter of vacuum, more complete than anything we can produce in laboratories on Earth. It is so sparse that the spacecraft might not encounter another solid object for millions of years. That emptiness defines the shape of our galaxy. The Milky Way is not crowded with stars. It is mostly space. The stars gather in a thin, luminous disk, spread so far apart that even light takes years to leap between neighbors. And yet, within that enormous space, our galaxy holds more stars than there are grains of sand on all the beaches of Earth. Around 400 billion suns shining within its boundaries. It is a number so large that the human mind can only approach it through comparisons. If you counted one star per second without sleeping or stopping, it would take more than 12,000 years to finish. If every person alive on Earth today were assigned an equal share, each would still have to count about 50 stars. These stars are not all the same. They come in a staggering range of sizes, colors, and ages. Some are hot and blue-white, burning their nuclear fuel quickly and dying after just a few million years. Others are small and red, glowing softly and steadily for hundreds of billions of years, long after our own sun fades away. Some contain barely enough mass to sustain fusion. Others hold dozens of times more matter than the sun, their cores dense and fierce beyond imagination. The differences are not only in size or temperature, but also in how these stars live together. Many stars exist in pairs, orbiting each other like slow dancers bound by gravity. Others gather in clusters, dense cities of light, where dozens or hundreds of stars share a common birthplace. In these crowded environments, gravity and radiation shape exotic phenomena, collapsing gas clouds, newborn stars, and bursts of ultraviolet light. Some stars pulse with perfect regularity, brightening and dimming in steady rhythms, like the beat of a galactic heart. Among this immense population, those 400 billion suns, there are at least 100 billion planets orbiting in regions where liquid water could exist. 100 billion potentially habitable worlds scattered across the Milky Way, Each one circles its star under different conditions, some too hot, some too cold, some perhaps just right. A few may host life, a few may harbor intelligence capable of wondering, just as we do, whether they are alone. Somewhere out there, another civilization could be watching their own robotic explorers drift into their version of the dark. The oldest stars in the Milky Way are ancient beyond comprehension. They formed more than 13 billion years ago, when the universe itself was still young, filled mostly with hydrogen and helium. Heavy elements like carbon, oxygen, and iron barely existed then. Those first generations of stars forged the raw materials that later built planets, oceans, and living things. Some of those early stars still shine today, quiet witnesses to the entire history of cosmic evolution. Around them, planets could have formed and developed life billions of years before Earth even existed. But the stars are not scattered randomly through space. They organize themselves into structure, a flattened disk about 1,000 light-years thick and 100,000 light-years wide. Our solar system sits embedded within that disk, about 26,000 light-years from the galactic center. When we look up on a clear night and see the Milky Way stretching across the sky, we are seeing along the plane of that disk, gazing through the dense concentration of billions of distant suns. Their combined light merges into a soft, glowing band that wraps the heavens. We cannot see the full shape of the galaxy from inside it, but we can feel its rhythm. Our sun orbits through this disk, passing regions of greater and lesser density, moving through lanes of gas, dust, and star fields. The glow we see is the integrated light of countless stars, most too faint to see on their own, but together bright enough to remind us that we live inside something vast and ancient. The Milky Way's visible form, the glittering disk that fills our night sky, is only the beginning. Beyond the light, beyond the edge of sight, its true extent stretches into invisible domains, shaped by gravity, filled with unseen matter, and linked to the greater structures of the universe beyond. Our galaxy turns slowly, like an immense pinwheel of stars drifting through space, but its spin doesn't follow the simple rules of a solid object. When a record spins on a turntable, every part completes one rotation in the same amount of time the center and the edge move together. The Milky Way doesn't behave that way. Stars near its center race around faster than those farther out, like runners on a circular track where the inside lanes move more quickly than the outer ones. Our solar system, sitting about 26,000 light-years from the center, takes roughly 250 million years to complete one full orbit. Astronomers call this span of time a cosmic year. Since Earth formed about 4.5 billion years ago, our planet has made only 18 of these long trips. In all of geological and biological history, from the first solid crust to today, Earth has turned around the galactic center fewer than 20 times. This enormous timescale reshapes our sense of history. When Earth last occupied this same spot in its orbit, the continents were joined into a single landmass called Pangaea. Dinosaurs did not yet exist. The land was covered with ferns and primitive reptiles. Mammals, flowers, and grass had not appeared. The dinosaurs' entire reign, from their rise to their extinction 65 million years ago, lasted only about 1/4 of one galactic year. Human civilization, from its first settlements to the present, spans less than 1/100,000th of a cosmic year. If we compress the galaxy's rotation into a single calendar year, everything humans have ever done would take place in the final seconds before midnight on December 31st. Because of this slow rotation, Nothing in the sky stays fixed forever. The stars we see as constellations form patterns that seem permanent, but they are temporary. Over millions of years, those shapes will shift and fade as the stars move along their own orbits. Our sun drifts with them, weaving through the galaxy's disk in a complex motion. It doesn't stay at a constant height. Instead, it oscillates up and down through the galactic plane, rising above it for about 33 million years, then descending below it for another 33 million. Each full cycle of this vertical motion takes about 66 million years. Some scientists have noticed that this up and down rhythm may align with certain mass extinctions in Earth's past. When the solar system passes through the dense midplane of the galaxy, it may encounter higher concentrations of dust, gas, and gravitational disturbances. Those interactions could send comets from the outer solar system tumbling inward toward the planets. Whether this link is coincidence or consequence remains uncertain, but it reminds us that our motion through the galaxy is not a calm drift. It's a journey through a living, changing environment. The Milky Way's rotation is not uniform. Astronomers call this complex motion differential rotation. Each part of the galaxy moves according to the gravity it feels from the mass inside its orbit. Closer to the center, where the density of stars and gas is higher, orbits are faster. Farther out, they slow. At the exact heart of it all lies the most powerful object in our galactic neighborhood, Sagittarius A*, the supermassive black hole at the center of the Milky Way. Sagittarius A times contains the mass of about 4 million suns packed into a space smaller than our solar system. Its gravity is so intense that it bends the very shape of space-time. It keeps the entire galaxy bound together, its invisible pull anchoring 400 billion stars in orbit. Near the black hole's edge, the event horizon space itself is twisted. Time slows there, compared to here. A clock placed near Sagittarius A times would tick more slowly than one on Earth. We can't see the black hole directly. It swallows light, along with everything else that strays too close, but we can see its influence. Stars that venture near it whip around at tremendous speeds, some reaching over 3,000 miles per second. They trace small, fast loops that reveal the mass hidden at the center. Their orbits, measured carefully with infrared telescopes, proved once and for all that a supermassive black hole lurks there. Occasionally, Sagittarius A times feeds. When a cloud of gas or an unlucky star drifts near, the black hole's gravity tears it apart. The debris spirals inward, forming a bright disk that heats to millions of degrees. Before the material vanishes beyond the event horizon, it glows in X-rays and radio waves, releasing energy visible from across the galaxy. Then, silence again, the meal finished, the center dark once more. Recent observations show that Sagittarius A times spins rapidly, perhaps near the maximum speed possible for any black hole. Its rotation is so fast that it drags the fabric of space around with it, a phenomenon known as frame dragging. Einstein's general theory of relativity predicted this effect more than a century ago, and now it has been confirmed in the most extreme laboratory nature provides. This immense object likely began as a smaller black hole early in the galaxy's history and grew by consuming gas, dust, and stars over billions of years. Its growth helped shape the Milky Way itself, pulling matter inward and setting the rotation of the spiral arms that define our galactic form. The region around the galactic center is anything but calm. It's a place of violence, blazing radiation, tangled magnetic fields, and stars packed close together in chaotic orbits. Many of those massive stars live short lives, exploding as supernovas and flooding the region with shockwaves and heavy elements. It's a cosmic storm, a place too intense for planets to form or for life to survive. Even at our distance of 26,000 light years, we remain bound to that center. Its gravity holds our sun, the planets, and all the stars of our neighborhood in place, guiding us along our slow orbit around the core. We are part of the grand structure it commands, a flattened disk of dust, gas, and light rotating around a silent, unseen power. Yet Sagittarius A times is only one part of a larger story, one piece of the intricate machinery that gives the Milky Way its shape, its motion, and its enduring beauty. We face a challenge that no astronomer studying another galaxy will ever experience. We live inside the very object we're trying to understand. Every other galaxy in the universe can be seen from a distance, photographed in full, mapped with clarity, studied as a single, complete structure. But for us, the Milky Way is both home and mystery. We must infer its shape and size while trapped within it, gathering clues from every direction, but never able to step outside for a look. It's like trying to map an entire city while confined to a windowless basement. You could send messengers to different streets and neighborhoods, but you'd never see the full skyline, never know exactly how the streets connect. That is our situation. We are cosmic cartographers working blind from the inside. When we look toward the center of our galaxy, our line of sight passes through the dense disk where most of the stars and gas reside. Between us and the core lies a vast stretch of interstellar dust and molecular clouds, thick, dark, material that absorbs visible light. It's like staring into fog. The further you look, the less you see. Ordinary light can travel only a few thousand light years before vanishing into the haze. Beyond that, the Milky Way's heart disappears into shadow. Astronomers have learned to use other kinds of light to pierce this darkness. Radio waves and infrared light can slip through dust that blocks visible wavelengths, allowing us to probe deeper into the galaxy's structure. Yet even these tools don't give us a perfect view. Our edge-on perspective means that when we look across the plane of the galaxy, we see the combined light of billions of distant stars overlapping each other. Their glows merge into the bright, milky band that arcs across the night sky. The sheer number of overlapping stars erases any clear sense of depth. It's like staring through an endless crowd. Individual faces blur into one bright, indistinct glow. Still, being inside the Milky Way has advantages. From our position within, we can study nearby stars in extraordinary detail, measuring their temperatures, compositions, and motions with precision. We can examine clouds of gas and dust up close, track how stars are born and die, and even detect planets orbiting distant suns. Astronomers who study other galaxies can see their shapes, but they can't see this level of intimacy. We trade the big picture for the small details, and from those details, we reconstruct the whole. One of the greatest tools helping us do this is the Gaia spacecraft, launched by the European Space Agency. Gaia has measured the positions and motions of over 1 billion stars, building the most detailed three-dimensional map of our galaxy ever made. By watching how stars move, we can trace the gravitational architecture of the Milky Way, its spiral arms, its central bar, and its hidden mass. The results are breathtaking. A living map of our galactic neighborhood, drawn not from images, but from motion and mathematics. And yet, we will never see our galaxy from the outside. We will never have the distant vantage point that reveals its spiral arms curling gracefully through space. We are permanent residents, forever within its boundaries. We are like beings living in a vast mansion, able to explore room by room but never step outside to admire the full structure. This limitation makes one of our greatest discoveries even more remarkable. Those elegant spiral arms that define our galaxy's beauty aren't solid structures at all. They are patterns, not things. They are regions where matter temporarily gathers and then moves on, like waves on the surface of the sea. For much of the 20th century, people imagined the Milky Way's arms as fixed, sweeping shapes, giant limbs of stars and dust rotating together like the blades of a fan. But that picture was wrong. Spiral arms are more like cosmic traffic jams. The stars and gas within them do not stay there permanently. They crowd together for a while, then drift apart. Imagine looking down at a highway from above. You might see a slow-moving stretch of traffic that seems solid and unchanging, but no single car stays there for long. Vehicles enter from behind and leave ahead, while the congestion itself keeps its general shape and location. That's what happens inside our galaxy. The spiral arms are not objects, but waves of compression that move through the disk. As these density waves sweep along, they squeeze clouds of gas and dust, triggering the birth of new stars. The newborn stars are hot and bright, brilliant blue-white beacons that make the spiral arms visible across tens of thousands of light years. Their light outlines the shape of the wave, just as headlights mark the shape of a distant traffic jam at night. But these luminous stars burn out quickly, dying as supernovas within a few million years, long before they can drift away from the arm that birthed them. That constant cycle of creation and destruction maintains the glowing shape we see, even though the individual stars are always changing. Our own solar system is not part of a major spiral arm. We reside in a smaller spur known as the Orion Arm, tucked between two of the galaxy's larger arms, the Sagittarius Arm and the Perseus Arm. We last crossed a major spiral arm about 50 million years ago, when Earth's continents looked different and mammals had only just begun to diversify after the dinosaurs vanished. We won't pass through another arm for about 10 million years. Each time we do, our system encounters denser regions of gas and dust, which may subtly affect the solar environment, perhaps even influencing Earth's long-term climate and biology. The spiral structure of the Milky Way moves much more slowly than the stars themselves. The stars orbit the center of the galaxy faster than the spiral pattern rotates, which means they pass in and out of these arms over time. This difference in speed is essential. If the arms moved at the same rate as the stars, they would wind tighter and tighter until the entire spiral vanished within a few 100 million years. Instead, the pattern persists, constantly refreshed by waves of compression and star formation. What drives and sustains this grand design remains a subject of debate. Some astronomers suspect that gravitational interactions with smaller satellite galaxies like the Sagittarius dwarf galaxy may stir the Milky Way's disk, feeding energy into the spiral waves and keeping them alive. Others believe the central bar of stars that runs through our galaxy's core acts as a kind of engine, generating ripples that propagate outward to form the arms. Recent observations reveal that our spiral pattern is not simple. It branches and twists, filled with spurs, gaps, and overlapping structures that evolve over tens of millions of years. Some arms fade while others strengthen. New branches appear, old ones merge or dissolve. The Milky Way is not a rigid mechanism, but a living system, constantly reshaped by gravity, motion, and time. And as grand as these spiral arms seem, these glowing rivers of starlight winding through space, they are only the most visible layer of something even greater. Beneath their beauty lies the full complexity of a galaxy still gathering, colliding, and transforming across billions of years, a structure so vast that we can never step back far enough to see it whole, yet close enough to feel its motion every second of our lives. Our galaxy does not drift through the universe alone. It moves as part of a quiet procession, surrounded by smaller companions that orbit it like faint moons around a planet. When you zoom far enough out, beyond the bright disk of stars that defines the Milky Way, a delicate network of smaller galaxies becomes visible, tiny, shimmering clouds of light caught in the pull of our gravity. Each of these systems is its own miniature galaxy, with millions or even billions of stars. Yet all are bound to us by invisible threads of gravitational force stretching across hundreds of thousands of light years. The most famous of these companions are visible from the southern hemisphere. The Large Magellanic Cloud and the Small Magellanic Cloud hang in the night sky as pale smudges of light, like torn pieces of the Milky Way drifting nearby. To early sailors navigating the southern oceans, these glowing patches served as guides across the vast sea. They had no idea that these clouds were entire galaxies orbiting our own. The Large Magellanic Cloud contains around 10 billion stars and lies roughly 160,000 light-years away. The Small Magellanic Cloud is smaller, home to about 3 billion stars, and sits around 200,000 light-years distant. Both exist well beyond the visible edge of our galactic disk, yet still within the reach of our galaxy's enormous dark matter halo. Their orbits are not smooth or peaceful. The Milky Way's gravity grips them tightly, distorting their shapes and stretching their stars into long, luminous trails. Streams of gas and dust flow from the Magellanic Clouds, pulled free by tidal forces, forming enormous ribbons that wrap around our galaxy. These streams are visible in radio wavelengths as faint arcs of hydrogen gas that stretch across nearly the entire southern sky. They are silent witnesses to the slow violence of gravity, a process that reshapes galaxies over billions of years. The Magellanic Clouds are only the brightest and largest members of a much greater galactic family. More than 30 smaller satellite galaxies orbit the Milky Way, scattered through space like drifting embers. Many are so dim that they cannot be seen with ordinary telescopes. Astronomers have discovered them only in recent decades using ultra-sensitive digital surveys. These galaxies carry names drawn from the constellations where they appear: Draco, Sculptor, Fornax, Carina, Ursa Minor. Most contain only a few million stars, faintly glowing against the background of the Milky Way's light. Some are almost entirely made of dark matter, their visible stars forming only a thin, ghostly trace over a hidden gravitational core. Our galaxy's gravity slowly unravels these small neighbors. As they move through our extended halo, tidal forces stretch and tear them apart. Their stars spill outward, forming long, faint streams that wrap around the Milky Way's outskirts. Over cosmic time, this process acts like a slow form of galactic cannibalism. The Milky Way grows not by forming new stars alone, but by consuming its smaller companions, absorbing their material and adding it to its own. The evidence is written across the sky, subtle arcs of stars invisible to the naked eye, but clear in deep surveys of the galactic halo. Some of those streams, such as the Sagittarius stream, trace the remains of galaxies that were swallowed long ago. This process is not unique to the Milky Way. Across the universe, large galaxies feed on smaller ones, gradually building their mass through mergers and tidal stripping. It's part of how galaxies evolve. The one we inhabit today is a mosaic of many that came before, a collection of remnants gathered under one gravitational umbrella. At the heart of this system lies something far larger than we can see. Observations show that the Milky Way's dark matter halo extends almost 2 million light-years from the galactic center, about 20 times farther than the visible edge of the stellar disk. That means the galaxy we know, the glowing band that crosses our night sky, is only a small kernel within an enormous, invisible sphere. If you were to imagine our visible galaxy as a cherry pit, the surrounding dark matter halo would be the size of a basketball. The cherry pit contains the 100,000 light-year wide disk of stars, gas, and dust, the Milky Way, as we can observe it. The basketball represents the true scale of our galactic domain, a massive, diffuse halo filled with dark matter particles that neither emit nor absorb light, yet outweigh all visible material by a factor of 10. Astronomers estimate that the halo holds somewhere between 600 billion and 3 trillion solar masses, a mass so great that it defines the very shape and behavior of our galaxy. We live deep inside this invisible ocean, unaware of its constant presence. Like creatures living in the sunlit layer of a deep sea, we see only the glowing surface above us, not the vast dark waters extending below. The stars, planets, and nebulae we know occupy a thin, bright layer, while the true structure of our galaxy stretches far beyond the reach of visible light. This unseen halo governs almost everything about the Milky Way's behavior. It controls how stars orbit, how galaxies interact, and how matter flows in and out of our system. The Magellanic Clouds and other satellites follow curved, looping paths through this dark medium, influenced by gravity from matter they cannot see. By studying their orbits, astronomers can map the shape and density of the halo, much as you might trace the shape of wind by watching how leaves move. Computer simulations have revealed that this halo is not smooth, but filled with countless smaller clumps known as subhalos, dense concentrations of dark matter that move through the larger structure like fish through the sea. Some of these subhalos may have captured enough normal matter to form small, faint galaxies of their own. Others remain completely dark, invisible but massive enough to tug subtly on nearby stars. These structures reveal that our galaxy is not static, but alive with motion and invisible complexity. The influence of the halo extends beyond our immediate neighborhood. Its gravity reaches far into intergalactic space, capturing thin streams of hydrogen gas drifting between galaxies. That gas becomes the raw material for new stars, feeding the Milky Way's slow but steady growth. The halo also acts as a kind of gravitational buffer, deflecting smaller objects and cosmic debris that might otherwise disrupt the delicate balance of our disk. Defining where this halo ends is nearly impossible. Its density thins gradually, blending into the faint dark matter background that fills all of space. There is no clear edge, only a slow fading from the realm of our galaxy into the general fabric of the cosmos. The Milky Way's influence doesn't stop abruptly. It simply becomes one thread among many in the grand cosmic web that binds galaxies together. Beyond this invisible envelope, space does not empty out, it connects. The gravity of the Milky Way interacts with that of nearby galaxies, shaping the structure of our local group, a small cluster of galaxies that includes Andromeda, Triangulum, and dozens of dwarfs. Within this group, our galaxy moves not as an isolated island, but as one current in an ocean of motion. The dark matter halo that surrounds us is both a boundary and a bridge, holding us together while linking us to everything beyond. Our galaxy is not the calm, perfectly balanced spiral we often imagine. It is a restless, living structure, bending, flexing, and shifting as it spins through the dark. The Milky Way wobbles like a coin losing its balance. its outer edges rippling up and down as gravity tugs from every direction. These slow undulations, spreading inward across hundreds of thousands of light years, form waves that travel through the galactic disk, changing the positions of stars and clouds like ripples crossing the surface of a pond. For a long time, astronomers assumed the Milky Way's disk was flat, but with more precise measurements, especially from surveys of variable stars, they discovered that the edges curve noticeably, rising above and below the plane of the galaxy. This warp is not static. It slowly precesses, or rotates, in the opposite direction to the motion of the stars. The rate is minute, about 1/1200th of a degree every million years, but over cosmic time, it reshapes the entire structure of our galaxy. This odd, wobbling motion reveals something deep about what lies beneath our galaxy's luminous skin. The cause, scientists believe, comes from the Milky Way's invisible framework, its dark matter halo. Computer models show that this vast halo is not a perfect sphere, but slightly flattened, shaped more like an American football than a ball. The stars of the Milky Way rotate inside this oblate, invisible mass, and the mismatch between the disk's rotation and the halo's symmetry creates gravitational torques that make the galaxy wobble. It's a cosmic version of a spinning coin. As a coin slows, it begins to tilt and oscillate, tracing small circles before falling flat. The Milky Way does something similar, not from friction, but from the subtle gravitational imbalance between its visible disk and its dark matter envelope. This constant tug causes the disk to flex, ripple, and twist as it spins, and the motion propagates across tens of thousands of light years. These waves affect everything inside the galaxy. Stars in the outer regions move up and down like surfers riding long, slow swells. Giant clouds of gas compress and stretch as the disk flexes around them, triggering bursts of star formation in some regions while scattering material in others. Even our solar system, sitting relatively close to the galactic center, participates in this gentle oscillation. Though the motion is far too slow for us to feel, the sun and its planets follow the warped shape of the Milky Way, like passengers on a ship rising and falling with the waves. This galactic wobble gives astronomers rare insight into the unseen matter that governs our galaxy's dynamics. By tracking how the warp precesses, how fast it turns, how its angle shifts, scientists can infer the shape and density of the dark matter halo. In effect, the Milky Way's slow motion acts like a seismograph for gravity itself, recording the pull of invisible mass. It is one of the few ways we can study dark matter on galactic scales, using the dance of stars to feel the contours of what cannot be seen. But our galaxy's motion is not shaped by the halo alone. The Milky Way's satellite galaxies, the large and small Magellanic Clouds, and dozens of smaller companions add their own gravitational tugs. As they orbit, they exert subtle but persistent forces that disturb the galactic disk, amplifying or changing the pattern of the warp. Their interactions create new waves, new twists, new oscillations that ripple across the Milky Way's body. Over time, these combined effects make our galaxy a constantly evolving system, flexing under the influence of both visible and invisible matter. This state of motion is not temporary. It's the normal life of a galaxy. Nothing in the universe stands still, not even on the grandest scales. The Milky Way bends and breathes as it rotates, its outer stars tracing spirals through space, while its dark halo sways around them. Yet even this complex, delicate balance is not permanent. Far ahead in cosmic time, something larger waits a transformation that will reshape both our galaxy and its nearest neighbor. Roughly 4.5 billion years from now, a slow-motion collision will begin. The Andromeda Galaxy, our closest large companion, is hurtling toward us at about 250,000 miles per hour. Andromeda contains more than 1 trillion stars, twice as many as the Milky Way, and it is only about 2.5 million light-years away, a small distance in cosmic terms. On clear nights, it already appears as a faint oval smudge in the constellation Andromeda, just visible to the naked eye. It looks peaceful, but it's moving straight toward us. The future of both galaxies is already written in their shared gravity. As Andromeda draws closer, its pull will begin to distort our galaxy long before the two collide. The Milky Way's outer spiral arms will stretch and twist, sending long streams of stars arcing into intergalactic space. Over millions of years, the two galaxies will begin to bridge the gap between them, their stars forming tenuous filaments of light that connect across the void. Then, after billions more years, the collision itself will unfold a slow, majestic merging unlike any event we can easily imagine. Despite its violent scale, the event will not resemble an explosion. Space between stars is so vast that direct collisions between them will be extremely rare. Instead, the encounter will be a gravitational storm, orbits scrambled, stellar paths reshaped, entire systems flung outward or inward as the two galaxies pass through each other again and again. Over time, they will lose their spiral forms, merging into a single, elliptical galaxy that some astronomers have already named Milkomeda, a hybrid born from the ruins of two great spirals. Our sun, by then nearing the end of its own life, will almost certainly survive the merger, but its fate is uncertain. Some simulations suggest the solar system may be thrown far into the outskirts of the new galaxy. Others predict it might even be ejected entirely, cast adrift into intergalactic space. If that happens, Earth, if it still exists, will orbit in a cold, dark solitude, circling a star with no galactic home. The collision between the Milky Way and Andromeda will last for billions of years, unfolding so slowly that no single generation of life could ever witness it. Yet, it is one of the most predictable events in the universe, a cosmic inevitability written into the fabric of gravity itself. Even as our galaxy wobbles and flexes today, it is already on course for that grand union. What we see in the night sky, the quiet band of the Milky Way arcing above us, is just a momentary shape in a structure that has always been changing and always will. When the Milky Way and Andromeda finally collide, the event will not end with the destruction of stars, but with their rearrangement into something entirely new. Over billions of years, the centers of both galaxies, each containing a supermassive black hole, will spiral inward toward one another, circling closer as they lose energy through the emission of gravitational waves. Eventually, the two will merge, forming a single black hole with a mass greater than 5 million suns. That collision between black holes will unleash a burst of energy unlike anything else in our galaxy's history. The waves of distorted space-time it produces will ripple outward, traveling across the universe. For a brief moment, those invisible vibrations will release more energy than our sun will emit in light during its entire 10 billion year lifespan. To any distant civilization watching with sensitive instruments, it will be a silent but unmistakable signal, the merging of two great galaxies, echoing through the cosmos. Afterward, the combined galaxy nicknamed Milkomeda will look nothing like its parent spirals. The graceful arms of both the Milky Way and Andromeda will vanish, replaced by a vast, glowing ellipse of stars. It will be an elliptical galaxy, smooth and football-shaped, with little sign of the swirling patterns that once defined us. Stars will move in random orbits rather than ordered circles, their paths determined by the gravitational chaos of the merger. It will be quieter, dimmer, and older, a cosmic remnant of two galaxies that once spun with youthful energy. But this grand collision is only one chapter in a far larger story. Even as we drift toward Andromeda, both galaxies are themselves being pulled towards something greater and more mysterious. Our entire local group, a small collection of galaxies, including the Milky Way, Andromeda, and dozens of dwarfs, is hurtling through space at nearly 600 miles per second. We are all moving toward a gravitational anomaly known as the Great Attractor. The Great Attractor lies about 150 million light-years away, in the direction of the constellations Hydra and Centaurus. It cannot be seen directly. The dust and stars of our own galactic plane obscure it, hiding it behind a region astronomers call the zone of avoidance, a part of the sky so filled with foreground light and material that visible telescopes cannot peer through it. But we can feel its pull. Thousands of galaxies across hundreds of millions of light-years are drifting toward the same point, drawn by the immense gravity of something hidden in that direction. Measurements show that the Great Attractor contains the mass of tens of thousands of Milky Way-sized galaxies, concentrated within a region roughly 500 million light-years wide. This immense structure acts as a gravitational anchor for a huge portion of our observable universe. The galaxies around it, including ours, move like leaves caught in a vast, invisible current. Yet even now, the full nature of the Great Attractor remains uncertain. When astronomers add up all the visible clusters in that region, such as the Norma, Centaurus, and Hydra clusters, they still fall short of the total gravitational influence observed. Something unseen must account for the rest, perhaps dark matter on a colossal scale, or entire galaxy clusters still hidden behind the veil of our own Milky Way. This means that our motion through space is not random. The Milky Way, Andromeda, and every other galaxy near us follow gravitational flows established by the largest structures in the cosmos. We are part of a cosmic river, drawn toward distant concentrations of mass that shape the motion of everything within reach of their gravity. Beyond the Great Attractor lies something even more enormous: the Shapley Supercluster, a vast collection of thousands of galaxies that may be the ultimate destination of our journey through space. The Shapley Supercluster's combined mass dominates an entire region of the universe, its gravity influencing not just our local group, but the motion of galaxies across hundreds of millions of light-years. On cosmic scales, the universe is not static. It is a restless web of attraction and flow, with every galaxy caught in motion around unseen centers of mass. While we are being drawn outward toward those colossal structures, another drama unfolds much closer to home. Our own galaxy acts as a predator, feeding on smaller neighbors that stray too near. One of the clearest examples of this process is the Sagittarius Dwarf Elliptical Galaxy, a modest system containing about 4 billion stars. It is currently being torn apart as it passes through the Milky Way's disk. Each orbit strips away more of its stars, stretching them into long, luminous streams that wrap around our galaxy like faint rings of light. These stellar streams form graceful arcs across the sky, invisible to the naked eye but revealed in deep astronomical surveys. They trace the path of the Sagittarius Dwarf as it slowly dissolves under our gravitational influence. Every time it swings through the dense regions of the Milky Way, tidal forces pull more stars free, leaving behind faint trails that encircle the galactic halo. Over billions of years, the dwarf galaxy will vanish completely, its stars becoming part of our own population, absorbed into the Milky Way's structure until no trace of its origin remains. This slow act of galactic cannibalism has happened many times before. The smooth distribution of stars in our halo, the faint, spherical region surrounding the galactic disk, is built from the remains of dozens or even hundreds of smaller galaxies that were captured and destroyed over the past 10 billion years. What appears to be a continuous cloud of stars is, in truth, a blend of ancient remnants. The process continues even now. The Large Magellanic Cloud, our most prominent satellite galaxy, may not be on a stable orbit at all. Recent measurements suggest it could be making its first close approach, having recently fallen under the influence of the Milky Way's extended dark matter halo. Over the next few billion years, as it spirals inward, our gravity will begin stripping away its stars and gas. Its final disintegration will seed new bursts of star formation within the Milky Way, as its gas becomes raw material for new suns. Even smaller companions, the ultra-faint dwarf galaxies that contain only a few thousand stars, bear scars of this same violence. Their elongated shapes and disrupted stellar patterns reveal that they too are being torn apart, piece by piece, by the Milky Way's gravity. Some are already little more than smudges of stars, halfway between galaxy and debris field. This cycle of destruction and creation defines how large galaxies grow. They do not simply collect gas from intergalactic space. They expand by consuming the smaller systems around them. The Milky Way's history is written in these acts of absorption, its structure built from countless mergers and tidal encounters. Even as we orbit toward Andromeda and drift toward the Great Attractor, we continue to feed, shaping and reshaping ourselves through gravity's slow, relentless work. In this way, our galaxy's past, present, and future are all connected by the same principle: motion guided by mass, attraction shaping form. From the merging black holes at its center to the faint dwarf galaxies dissolving at its edges, the Milky Way exists in a state of continuous transformation, one chapter in a cosmic story that never truly ends. For much of the 20th century, astronomers weren't sure whether the Milky Way possessed one of the most common and influential structures seen in spiral galaxies across the universe, a central bar of stars. In other galaxies, these stellar bars stretch outward from the core like the handle of a cosmic dumbbell, made of billions of stars orbiting together as a single, rotating structure. They act like engines of galactic evolution, pulling gas toward the center, feeding star formation, and shaping the spiral arms that twist outward through the galactic disk. Yet for decades, no one could prove whether our own galaxy had one. The challenge lay in our perspective. We live inside the Milky Way's disk, surrounded by its stars and veiled by thick clouds of interstellar dust. Trying to detect the galaxy's overall shape from here is like trying to map the outline of a forest while standing among the trees. The densest regions of the Milky Way, the parts we most needed to see, were hidden behind curtains of cosmic soot that absorb visible light. The galactic center, in particular, sat behind a band of darkness so deep that even the most powerful optical telescopes could not pierce it. That changed in 2005, when the Spitzer Space Telescope began observing the sky in infrared light. Unlike visible light, infrared wavelengths can pass through dust, allowing astronomers to peer into the obscured heart of the galaxy. When Spitzer turned its sensitive detectors toward the Milky Way's center, it unveiled something remarkable. Our galaxy does have a central bar, a massive, elongated structure spanning roughly 27,000 light years from end to end. Billions of stars form this glowing bar, rotating together around the galactic core. in a coordinated sweep. This discovery explained many of the puzzling behaviors astronomers had observed in the Milky Way for years. The bar acts as a gravitational engine, stirring the material in the galactic disk and driving the formation of our spiral arms. As the bar rotates, it sends out waves of compression that sweep through the gas clouds in the surrounding disk, triggering the collapse of dense regions and igniting bursts of new star formation. It also channels gas and dust inward toward the supermassive black hole at our galaxy's core, Sagittarius A*, providing the fuel that occasionally flares into powerful outbursts of radiation. The bar itself rotates faster than the rest of the galaxy. It completes one full revolution roughly every few 100 million years, meaning that different regions of the Milky Way periodically align with its gravitational influence. When that happens, stars and gas clouds feel its pull, creating temporary waves of star formation that ripple outward through the spiral arms like pulses of light. Over time, this bar changes shape. As it transfers angular momentum to the surrounding disk, it gradually lengthens and becomes more pronounced. Simulations suggest that it may have formed only a few billion years ago, relatively recent in galactic terms. It's a young feature by cosmic standards, but one that profoundly influences our galaxy's evolution. What once seemed like a simple spiral turns out to be a barred spiral, a more complex and dynamic organism than anyone had imagined a century ago. Within this immense structure, the Milky Way continues to breathe, creating and extinguishing stars in a steady rhythm. Across its vast expanse, about 3 new stars ignite every year, while roughly 2 reach the end of their lives. This quiet balance has persisted for over 10 billion years, slowly transforming the raw hydrogen and helium that once filled our galaxy into heavier elements: carbon, oxygen, silicon, iron, the ingredients of rocky planets and living organisms. Every atom in our bodies, apart from hydrogen, was forged in the nuclear hearts of long-dead stars. We are, quite literally, made from their ashes. Star formation, however, does not occur evenly throughout the Milky Way. It happens mainly within the spiral arms, where waves of compression squeeze cold clouds of gas until they collapse under their own gravity. Within these dense regions, newborn stars flare to life, illuminating their surroundings and forming clusters that glow like scattered jewels across the galactic plane. These glowing nurseries are among the most beautiful and energetic regions in the galaxy. The most massive of these newborn stars live fast and die young. Containing between 10 and 100 times the mass of the Sun, they burn through their nuclear fuel in just a few million years before dying in supernova explosions. Each explosion releases more energy in a few seconds than our Sun will emit over its entire lifetime. These supernovas do more than destroy their parent stars, they shape the galaxy. Their shockwaves plow through nearby clouds, compressing gas and triggering new rounds of star formation, continuing a self-sustaining cycle of creation and destruction. Smaller stars like our Sun live much longer, burning their fuel steadily for billions of years. When they near the end of their lives, they swell into red giants, shedding their outer layers before collapsing into white dwarfs, hot, dense remnants that slowly fade over time. These long-lived stars act as stable beacons of energy, offering the conditions where life might have time to evolve and flourish on orbiting planets. As each generation of stars forms and dies, it enriches the galaxy with heavier elements. The first stars, born soon after the Big Bang, consisted almost entirely of hydrogen and helium. When they exploded, they seeded space with heavier atoms, and the next generation of stars formed from this enriched material. Over billions of years, the Milky Way became chemically diverse, filled with elements that allowed complex molecules and eventually biology to emerge. Our sun, born about 4.6 billion years ago, belongs to at least the third generation of stars. It formed from gas that had already been cycled through multiple rounds of stellar birth and death. The planets of our solar system, including Earth, condensed from this recycled material, inheriting a chemical legacy billions of years in the making. In that sense, our world is a product of the Milky Way's long memory, assembled from the remains of stars that lived and died long before our sun existed. Today, the rate of star formation in the Milky Way has slowed dramatically. 10 billion years ago, our galaxy's youth was a time of feverish creation, with new stars forming perhaps 10 times faster than they do now. Over time, as more gas was locked into long-lived stars or expelled by supernova winds, the supply of raw material for new stars dwindled. The Milky Way, once blazing with youthful energy, now glows in middle age, a galaxy still vibrant, but quieter, more measured. Yet the process continues. Even now, deep within the spiral arms, cold clouds collapse, stars ignite, and the cycle of life and death turns once more. Each star that forms today carries within it the memory of those that came before the heavy elements, the chemistry, the dust. The Milky Way remains a place of ongoing creation, a self-renewing structure that recycles its matter across cosmic time. What we see when we look up at the night sky, the faint, milky band of light stretching across the darkness, is just the visible trace of this endless story. Billions of stars, at every stage of their lives, fill that band. Some are newly born, others are dying. Together, they weave the tapestry of a galaxy that, even now, continues to evolve quietly, gracefully, and without end. Our galaxy is still alive, with motion and light, but even galaxies age. Computer models suggest that the Milky Way will continue forming new stars for billions of years to come, though at a slowing pace. Each generation of stars consumes part of the galaxy's remaining gas, and that supply, once abundant and restless, is gradually running low. The spiral arms that today glitter with newborn stars will someday fade, their raw material gone. In time, the Milky Way will grow quiet. The great engines of stellar birth will fall still, leaving behind only the long-lived, cooling embers of the stars that once were. This future still lies far ahead. For now, the Milky Way remains a place of constant transformation, and its boundaries continue to surprise us. For much of the last century, astronomers thought the galaxy's stellar disk ended at a neat, well-defined edge, about 50,000 light-years from the center. Beyond that, they expected only darkness, a scattering of distant globular clusters, and the occasional rogue star drifting through the void. The galaxy, in their minds, had a tidy edge, clean and comprehensible. That picture has dissolved. In 2018, using the exquisitely precise data from the Gaia mission, astronomers discovered that the Milky Way extends far beyond that imagined border. Gaia's star catalog revealed stars belonging to the galactic disk as far as 84 to 103,000 light-years from the center, tens of thousands of light-years farther than anyone had believed. These distant stars are not wanderers. They move as part of the same flattened, rotating structure as our own sun, proving that the disk stretches deep into the outskirts of space. Follow-up studies soon pushed the boundary even farther. Observations now find stars at distances approaching 130,000 light-years, effectively expanding the known diameter of the Milky Way well beyond the century-old standard of 100,000 light-years. The familiar size of our galaxy, a number that appeared in textbooks and encyclopedias for generations, has become only an approximation. The true figure is larger, and possibly still growing as our instruments improve. But even this grand stellar disk is just the visible part of something far greater. Surrounding it, enveloping it completely, is the Milky Way's dark matter halo, a vast, invisible structure that stretches nearly 2 million light-years from the center, 20 times the reach of the visible stars. This halo extends almost halfway to Andromeda, our nearest large galactic neighbor. The idea that the Milky Way and Andromeda's halos might already touch or overlap changes how astronomers imagine their eventual collision. In a sense, the first contact between the two galaxies may have already begun, not through the meeting of stars, but through the mingling of invisible matter. This enormous reach creates deep puzzles. How can stars remain gravitationally bound at such distances, orbiting a center that lies hundreds of thousands of light-years away? A single orbit for these far-flung stars can take more than 1 billion years, meaning they have circled the galactic core only a handful of times since the Milky Way first formed. Their very existence challenges models of how galaxies stay stable over cosmic time. Part of the answer may lie in our galaxy's interactions with smaller companions. As the Milky Way captures and tears apart satellite galaxies, the stripped stars spread out, creating faint streams that wrap around the halo. Some of the distant stellar populations discovered by Gaia may belong not to the original disk, but to the remnants of ancient collisions, ghostly traces of galaxies long since consumed. The Milky Way, it seems, grows not just by gathering gas, but by absorbing the lives of smaller systems, scattering their stars across unimaginable distances. Each discovery pushes the map of our galaxy outward, and with every new generation of instruments, the Milky Way grows larger in our understanding. It may not even make sense to speak of a final edge. The galaxy's structure blurs gradually into the intergalactic medium, and the dark matter halo fades so slowly that there is no clear dividing line between ours and the space beyond. The universe, it seems, does not draw borders, and within this vastness, subtle forces continue to shape everything we see. Magnetic fields, invisible but powerful, weave through our galaxy like threads in a cosmic fabric. They are faint, thousands of times weaker than a refrigerator magnet, but they stretch across the entire 100,000 light-year width of the Milky Way. These fields guide the flow of charged particles, sculpt the behavior of interstellar gas, and even influence how stars are born and die. Imagine them as invisible highways of energy, spiraling around the galactic disk. The fields follow the same broad pattern as the Milky Way's spiral arms, wrapping around the center in vast, sweeping arcs. The rotation of the galaxy itself stretches and twists these fields, shaping them into a graceful spiral structure. In a sense, the magnetic field mirrors the motion of the stars, an unseen double of the visible galaxy. Charged particles called cosmic rays, launched into space by supernova explosions, race along these magnetic tracks. High-energy protons and electrons spiral through the fields, sometimes traveling thousands of light-years before striking anything. They move invisibly, but their paths trace the outlines of the magnetic web that fills the Milky Way. In some regions, these fields gather strength, forming filaments that can guide gas into long, narrow streams. In others, they weaken and disperse, allowing gravity to dominate and pull material into dense knots where stars can form. This delicate interplay between magnetism and gravity shapes the life of the galaxy. When field lines become tangled or compressed, they can both trigger and resist star formation, encouraging collapse in one place while holding it back in another. That balance helps explain why stars form in bright clusters along certain regions of the spiral arms, while other regions remain dark and quiet. To study these invisible structures, scientists turn to light itself. When dust grains floating in interstellar space align with local magnetic fields, they polarize the light that passes through them. By measuring this polarization, astronomers can infer the direction and strength of magnetic fields across vast distances. The Planck Space Observatory created one of the first comprehensive maps of the Milky Way's magnetism by measuring this effect, revealing an intricate lattice of fields threading through our galactic disk. These magnetic fields are born from motion. As clouds of ionized gas move through space, they carry electrical currents that create magnetic effects. The rotation of the Milky Way amplifies and organizes these currents, turning local disturbances into galaxy-wide patterns. In the dense, chaotic regions near the galactic center, where stars form and die in violent bursts, magnetic fields can be hundreds of times stronger than the average. Near the outer disk, between the spiral arms, they weaken until their presence is little more than a whisper. Even at their weakest, these fields hold the galaxy together in subtle ways. They influence how cosmic rays move, how gas collapses into stars, and how energy spreads across space. Sometimes, when the magnetic field lines snap and reconnect, a process known as magnetic reconnection, they release bursts of energy that can ripple through interstellar space. These events, though invisible to our eyes, help distribute heat and motion across the galaxy, linking our local environment to the wider electromagnetic currents of the universe. Through this invisible network, our galaxy connects to the cosmic web beyond. The same magnetic principles that shape the Milky Way also thread through clusters of galaxies and intergalactic filaments, hinting that the universe itself may be bound together by fields that stretch across unimaginable distances. Even as the Milky Way expands and evolves, its structure remains tied to this larger, unseen framework, a reminder that the space we inhabit is not empty, but alive with forces that never rest. And so, while stars form and fade, while the galaxy stretches and changes shape, the magnetic threads persist silent, patient, endlessly weaving the Milky Way into the grand electromagnetic fabric of the cosmos. Our galaxy, immense as it seems from within, is only a single island of light among a sea of billions. Astronomers now estimate that the observable universe holds roughly 2 trillion galaxies, each one a collection of stars, gas, dust, and dark matter, bound together by gravity. 2 trillion. The number is so vast that it almost loses meaning, a statistic that stretches the imagination until it blurs. If every galaxy were a grain of sand, the observable universe would be a cosmic desert stretching far beyond any horizon. The Milky Way is just one among this ocean of galactic cities, and in nearly every respect, it is ordinary. It contains about 400 billion stars, placing it near the middle of the cosmic scale. Many galaxies are smaller, fragile spirals, or irregular shapes with only a few million suns. Others, colossal ellipticals, hold more than 1 trillion stars, each ancient, bloated systems that make our home look small by comparison. Our galaxy's design, a luminous spiral with a central bar and sweeping arms, is one of the most common blueprints in the cosmos. Around 60% of known galaxies share this basic shape: a bulge at the center, a thin rotating disk, and bright arms coiling outward through space. In that sense, The Milky Way is typical, a single, shining node in a pattern repeated across the universe. But within that normalcy, there are subtleties that make our home unique. For one, we live in a quiet neighborhood. The Milky Way drifts through space in relative solitude, far from the chaotic hubs where galaxies collide and merge in spectacular bursts of light. Many galaxies are born and live in crowded clusters, dense environments where gravity pulls neighbors into constant encounters, twisting and reshaping them into warped, elliptical forms. By contrast, our part of the universe is calm. Aside from our future collision with Andromeda, we remain largely undisturbed. This isolation has allowed our delicate spiral structure to persist for billions of years, undamaged by the violence that transforms so many others. Chemically, too, we are ordinary. The Milky Way's stars contain typical amounts of heavy elements: carbon, oxygen, iron, the byproducts of countless generations of stellar evolution. These elements, forged in the hearts of dying stars, enrich each new wave of star formation, shaping the planets and potential life that follow. Our sun is slightly richer in metals than the galactic average, but not by much. Across the universe, there are millions of suns with similar compositions, and likely millions of planetary systems that share our chemical story. Still, the Milky Way sits at an interesting stage in its life. Astronomers describe galaxies by their colors: blue for those rich in star formation, red for those that have grown old and quiet, and green for those in between. Our galaxy lies in this green valley, meaning its star-making era is slowly winding down. The fuel for star formation, cold gas and dust, is being consumed faster than it is replenished. The bright blue spirals of our youth are fading to a gentler, older glow. When seen against the backdrop of the cosmos, these facts are humbling. Our galaxy, grand as it seems, represents less than 1/1,000,000th of the total galactic population. It is neither unusually bright nor unusually dark, neither the largest nor the smallest. It is a middleweight in a universe of giants and dwarfs, a single note in an endless symphony of creation. And yet, the Milky Way is part of something larger still. We do not float aimlessly through space. We move along one of the universe's most astonishing structures, the cosmic web. This web is the ultimate architecture of the universe, an immense network of dark matter filaments that stretch across billions of light years. These filaments are the skeleton of creation itself, connecting clusters of galaxies like the threads of an invisible tapestry. They are the highways of cosmic matter, channeling gas, dust, and galaxies through gravitational pull. Our galaxy lies embedded within one of these filaments, traveling along it much like a train following a track. The filament extends toward the Virgo cluster, a sprawling collection of over 1,300 galaxies located about 54 million light-years away. The Milky Way and its local group Andromeda, the Magellanic Clouds, and several dozen dwarf companions are all moving in this direction, drawn by the gravitational pull of the massive structures ahead. The cosmic web is not uniform. It consists of long, thread-like filaments separated by immense voids, regions so empty they contain almost no galaxies at all. The matter in the filaments accounts for roughly 60% of all the mass in the universe, both visible and dark. At the intersections of these filaments, galaxies gather into clusters and superclusters, the densest regions in existence. When viewed in simulations, the entire structure resembles a colossal neural network, with galaxies as points of light connected by tendrils of matter. Between these luminous pathways stretch the cosmic voids, the dark gaps between the bright nodes, vast, silent regions spanning hundreds of millions of light years. This intricate pattern did not appear all at once. It grew out of the primordial fluctuations that rippled through the early universe shortly after the Big Bang. At that time, matter was distributed almost evenly, but not quite. Tiny variations in density no greater than 1 part in 100,000 gave gravity something to work with. Over billions of years, those minute differences grew. Matter flowed toward the slightly denser regions, forming filaments and clusters. The result is what we now call the cosmic web, a structure so vast that no single image can capture it. Our galaxy's path through space follows this gravitational blueprint. We move along the dark matter filaments that once guided the flow of gas and radiation in the early universe. The Milky Way, Andromeda, and every galaxy we can see are strung along these invisible threads, moving through space, not randomly, but as part of an organized cosmic flow. Even the dark matter halos surrounding galaxies are shaped by the same pattern, merging and stretching in rhythm with the larger web. Between the galaxies and our filament lies the intergalactic medium, a thin gas heated to millions of degrees. Though almost unimaginably diffuse, just a few atoms per cubic meter, it fills the space between galaxies, glowing faintly in X-ray light. This hot gas acts as the connective tissue of the cosmic web, carrying energy and matter from one region to another. Over cosmic time, it provides the raw material for new galaxies to form and grow, feeding them through a slow, steady inflow. Recent observations and computer simulations have begun to map these filaments in detail. Using telescopes sensitive to X-rays and the gravitational bending of light, astronomers can trace the outlines of dark matter itself. As light from distant galaxies passes through the web, it bends slightly, a phenomenon known as gravitational lensing. By measuring this distortion, researchers can infer the density and shape of the invisible filaments that thread the cosmos. What they find matches theory. The Milky Way, like all galaxies, drifts along one of the universe's main structural highways. This understanding changes our perspective. We often picture our galaxy as an isolated island of stars adrift in darkness. In truth, it is part of a grander design, a vast, interconnected network stretching to the limits of the observable universe. The same gravitational forces that bind the stars of the Milky Way also tie our galaxy to its neighbors, to clusters millions of light years away, and to filaments that reach into cosmic depths beyond sight. The Milky Way is, in every sense, a citizen of this greater web. It lives within a system of relationships that spans the cosmos, shaped by ancient gravity and guided by the hidden geometry of dark matter. When we look at the faint band of our galaxy in the night sky, we are seeing one bright strand in a structure that binds together all galaxies, all light, and perhaps all time. The cosmic web is not merely a backdrop to our galaxy's story. It is the stage, the script, and the hidden machinery that shapes its every motion. The Milky Way does not evolve in isolation. It breathes in rhythm with the larger universe. Invisible filaments of dark matter and tenuous gas connect our galaxy to the vast intergalactic network, regulating the flow of material in and out of its spiral disk. Along these filaments, streams of cold gas fall inward, feeding the birth of new stars. At the same time, winds from supernova explosions and radiation from young, hot suns push matter back out, escaping along the same channels into intergalactic space. This constant exchange forms a kind of cosmic respiration. Our galaxy inhales raw material from the universe and exhales energy and enriched elements back into it. The process repeats endlessly, a galactic heartbeat that has pulsed for more than 10 billion years. When massive stars die, they return heavy elements, carbon, oxygen, iron to the interstellar medium. Those elements later condense into new generations of stars and planets, closing the great loop of creation. Some of this material escapes entirely, joining the intergalactic medium that stretches between galaxies. Even now, a fine mist of elements forged in ancient stellar furnaces drifts through space, waiting to seed other worlds yet unborn. If we could step outside our galaxy to a distance of several million light years, the sight would leave us breathless. The Milky Way would reveal itself as an immense, elegant spiral suspended in darkness, a pinwheel of light turning in the infinite night. Its arms would unfurl gracefully from a glowing central bulge, wrapping around the galactic core like ribbons of starlight. The spiral arms would shimmer with countless blue-white clusters, young, massive suns burning with fierce intensity, arranged like lanterns along cosmic highways. Between the arms, softer yellow light would glow from older, quieter stars, the long-lived citizens of our stellar city. The heart of the galaxy would blaze with concentrated radiance. There, billions of ancient stars form a dense, bar-shaped structure that rotates slowly around the supermassive black hole Sagittarius A*, whose gravity anchors the entire system. Surrounding this luminous core, dark lanes of interstellar dust would weave through the spiral arms like ink-brushed shadows, marking regions where new stars are still forming. If we looked in infrared light, these dark regions would blaze with heat, the hidden nurseries of creation, glowing with the energy of stars being born inside cocoons of gas. From ultraviolet to radio, each wavelength would reveal a different face of the Milky Way. In visible light, we would see its stars like a silvery river. In infrared, we would glimpse the heat of stellar birth. In radio waves, we would detect vast clouds of hydrogen spiraling through the disk. And in high-energy X-rays, we would witness the ghostly remnants of supernova explosions, the scars of stars that lived and died long before our sun was born. Each layer adds another dimension to the portrait, reminding us that beauty in the cosmos is not merely visual but multispectral, woven across the entire electromagnetic spectrum. Viewed edge-on, our galaxy would resemble a thin, glowing blade suspended in space, a cosmic pancake less than 1/50th as thick as its width. The galactic disk would warp gently near the edges, bending upward and downward like the rim of a record caught in slow motion. This warp, caused by the gravitational pull of the dark matter halo and nearby satellite galaxies, gives the Milky Way a living, breathing appearance, as though it were flexing in response to invisible tides. Surrounding this shining disk, we would see the faint halo, a sparse population of ancient globular clusters orbiting far above and below the galactic plane. Each cluster contains hundreds of thousands of old stars, their orbits tracing the true three-dimensional outline of our home. They would appear like glittering embers, flickering in the darkness, their collective light mapping the skeleton of the galaxy. Beyond them lies the immense, unseen sphere of dark matter, a structure so vast that it dwarfs the luminous Milky Way itself. Though invisible, its presence would be betrayed by the way it bends the paths of stars, holding them in motion against the centrifugal pull of their speed. Orbiting our galaxy like smaller moons, dozens of companion galaxies would shimmer faintly, The large and small Magellanic Clouds would appear as luminous patches trailing long ribbons of gas and stars torn loose by tidal forces. Streams of debris from other devoured companions, the remnants of the Sagittarius dwarf and others now lost to history, would arc across the sky like threads of spilled light. Each stream is a fossil record of a smaller world consumed by our own, its stars gradually merging into the Milky Way's population. And in the far distance, across the cosmic gulf, the Andromeda Galaxy would loom a mirror spiral, shining with the light of 1 trillion suns. Through deep, telescopic eyes, we would see its bright core and winding arms, and we would know that it is coming toward us. 4 billion years from now, its shape will fill our night skies, then merge with ours, fusing 2 galaxies into one. From that union will arise a new elliptical galaxy, a cosmic child born from the meeting of giants. But from this vantage point, in this era, Andromeda is still serene, a distant partner in an ancient, inevitable dance. Yet no matter how vividly we imagine it, we will never see the Milky Way from outside. We live inside its luminous fabric, like insects trapped within the stained glass window of a cathedral, able to study the colored patterns up close, but never to step back and see the full design. Our telescopes peer across thousands of light years. Our probes explore the edges of the solar system, but we remain bound within the walls of our own creation. This limitation defines both our fragility and our genius. We cannot escape the galaxy, yet we have learned to reconstruct it from within. Piece by piece, like archaeologists restoring a shattered mosaic, we have gathered light from across the sky and assembled a picture of our cosmic home. Every spectral line, every parallax measurement, every gravitational clue adds a tile to the image. The final picture is imperfect, but astonishingly complete. A spiral galaxy, 100,000 light years wide, containing 400 billion stars, wrapped in a halo of dark matter, orbiting within a filament of the cosmic web. To grasp even a fragment of this from the inside is one of the great triumphs of human thought. We have transformed starlight into knowledge. We have used mathematics to travel where our bodies cannot go. Our instruments have become extensions of our senses, our equations, extensions of imagination. Through them, the Milky Way, once a mysterious band across the night, has become a known place. Still, our understanding carries a quiet poignancy. We are both the observers and the observed, particles of the galaxy trying to comprehend the whole. The light that tells us of our home also passes through us. The atoms in our bodies were born in its stars. To study the Milky Way is, in a sense, to study ourselves, a species of dust, endowed with memory, tracing the story of the dust from which it came. From within this glowing disk, our entire history has unfolded. Civilizations have risen and vanished. Oceans have formed and evaporated. Species have appeared and disappeared, all while our solar system has drifted through the galaxy's vast spiral, completing less than one orbit in all of Earth's existence. The constellations we draw in our skies are brief patterns, shifting mosaics on a stage that moves too slowly for human eyes. And yet, from this fleeting vantage, we have reached for eternity. Our telescopes extend across oceans and deserts. Our spacecraft have left the solar system. Our signals now leak into interstellar space. The Milky Way, in a small but undeniable way, has become self-aware. Through us, it looks inward. Through us, it begins to understand its own structure. If we could step outside and look back, we would see a galaxy spinning quietly among billions of others, its arms glittering with starlight, its heart pulsing with ancient fire. Somewhere within one of those arms, a small yellow star glows faintly, circled by a handful of planets. On one of those worlds, tiny creatures look up and try to imagine the whole, and against every odd, they succeed. That is the miracle of perspective. We will never stand outside our galaxy, yet we can know it intimately. We are bound within it, but not blinded by it. The Milky Way is both our cradle and our creation, the vast cathedral in which we were born, and the structure we have learned to describe with numbers, maps, and poetry. We are the galaxy made conscious, a momentary flicker of thought in a sea of stars, asking the oldest and simplest question of all: what is this place, and how did we come to be within it? The answer, written in light, is all around us, spinning, shining, and still unfolding across the infinite night.